In this part, we will be looking at assigning RNS to another type of formulas, that is Fischer projections. Fischer projections are very common formulas that we usually use when it comes to amino acids or sugar compounds. Due to the fact that we have several chiral centers that can exist in the molecule, it makes it easier to actually do the Fischer projection to draw these structures and to be able to label them RNS without having to go back to the 3D formula. Fischer projections assigning RNS is going to follow a set of rules that are totally different from how we assign 3D configurations, RNS. So that's important to keep in mind. However, both formulas will share the same order when it comes to priorities. Will always depend on atomic number. So let's look at this compound. That's a 3D formula. The 3D formula, the way how we actually translate it to Fischer projection is basically keeping the carbons on the vertical line, starting with the most oxidized carbon, which is a CH2OH in this case, ending up with the least oxidized one, which is CH3 in this case. Having the hydrogen and the other group on the horizontal line. Horizontal line means pointing towards. So the Fischer projection will always be visualized as the horizontal line basically being up and vertical lines basically down. And this is why every single time we do a rotation, the final assignment will be the opposite to what the rotation is. Why? Because the fourth group is up. And you know already from the 3D formula, when we do the assignment of RNS, my fourth group, I want it to be in the back before I assign RNS. So making it the opposite direction will right away switch the final configuration. So let's take examples. So here is one. So the hydrogen being viewed on the left, OH is also up, so that's why it's right here. And the CH2OH on the vertical line ending up with a CH3. What is, I see here it's an R, but why is it an R? Which of those is going to have the highest in priority? Well, we know already the chiral center is in the one in the center, right here. So oxygen will be number 1. CH2OH will be number 2. CH3 will be number 3. And hydrogen is up. So it's counterclockwise. Hydrogen is up towards. What is that? Counterclockwise, hydrogen is towards. So that's an R configuration. It's an R configuration. So even though it's counterclockwise, I have to consider that the fourth group is up, is on the horizontal line. Let's take another example. You can see here clearly that we have Fischer projection, and I'm asked to assign the stereochemistry. All right, chiral center is the carbon in the middle. It has the 4 different groups. So what do I have? I have an oxygen, I have a carbon of a carbonyl, and I have a carbon of a methyl, and I have a hydrogen. What's the priority ranking here? Oxygen would be number 1, carbonyl carbon would be number 2, methyl would be number 3. So I have a clockwise, but the hydrogen is up towards. So clockwise, hydrogen is towards, so that's why it's an S configuration. So it's always going to be the opposite to what you end up basically having as a rotation. So that's something to keep in mind. So the 4 scenarios, and let me remind you here with the 4 scenarios of the 3D, and then I will mention the 4 scenarios of the Fischer projection. The 4 scenarios for the 3D, clockwise fourth group is away, that's an R. Counterclockwise fourth group is towards, that's an R. Counterclockwise fourth group is away, that's an S. Clockwise fourth group is towards, that's an S as well. That's if I'm dealing with a 3D configuration, 3D chemical formula. What if I'm dealing with a Fischer projection? Clockwise fourth group is up or towards, will always be basically S. And clockwise fourth group is away, we know it's going to be an R, but that's not going to happen when the hydrogen is on the horizontal line. What if the rotation is counterclockwise and the fourth group is up or towards? Well, that will be basically an R configuration. So keep that in mind. Fischer rules, usually you want to have the highest oxidized carbon on top and the vertical line to keep it for the carbons, and the other groups to be on the horizontal line. Now there is some rotation. Here's one of them, a 180-degree rotation. If I take this molecule, that's a Fischer projection, and I do 180-degree rotation for every single group, meaning the carbonyl or carboxylic acid goes down, methyl goes up, hydrogen goes on the right-hand side, and OH goes on the left-hand side. Let's do the labeling for this one, and let's do the labeling of the other. So oxygen first, so carbonyl next, so that's a counterclockwise. Hydrogen is up, so that's an R. How about this one? What do I have? Hydrogen, oxygen, carbonyl, so that's a counterclockwise. Hydrogen is up, so that's an R configuration as well. So that what do I get out of this? When I rotate a Fischer projection 180-degree, I will end up having the same exact compound. But if I rotate it 90-degree, let's see what we get out of this. We have OH, carbonyl number 2, so that's a counterclockwise. Hydrogen is up, so that's an R. Keep that in mind. I do 90-degree. What's a 90-degree? Carbonyl comes here, OH goes down, methyl goes to the left, and hydrogen goes up. So look at this structure now. Remember, this is an R configuration. How about this one? What do I have? Oxygen, carbonyl. So it's a counterclockwise, but the hydrogen is away now. Hydrogen is away. So when it's a counterclockwise and hydrogen is away, so that's an S configuration. So what happens when I rotate the Fischer projection 90-degree? I end up having the enantiomer of it. The enantiomer of it. So the take-home message here, Fischer projection, labeling will always be the same if I rotate the compound 180-degree. But the Fischer projection, if it goes 90-degree rotation, will result in having the enantiomer of it. And that's an example right here for you. Here's another example. You can see that we have an oxygen, an aldehyde, so it's a C double bond O. That's why this will be number 2, and the CH2OH will be number 3. So that's a counterclockwise. Fourth group is up towards, so that's why it's an R configuration. So keep that in mind. This is a Fischer projection that has 2 chiral centers, and I could easily do the labeling without having to go through the 3D chemical formula. So let's look at the one on the top. This carbon, Cl will be number 1. The bottom carbon will be number 2. So that's a clockwise. Clockwise hydrogen is up. So that's an S configuration. The one on the bottom, chloro would be number 1. Top carbon will be number 2. So that's a clockwise, but hydrogen is up. So that's an S configuration. So I have basically 2 centers. Both of them are S configuration. So keep that in mind, that you're always going to have to go through the 2 set of rules, that if the horizontal line where the 4th group is, you need to treat it as it is actually forward. It's towards you. So the clockwise will become an S, and the counterclockwise will become an R. That's how it is when it comes to the Fischer projection. Just like other structures that we've seen, how they can be diastereomers, like the cis and trans alkenes, we know they are non-mirror image of each other, and they are non-superimposable. That's why they are fit examples for diastereomers, or the cyclic alkanes as well. You can see here clearly that we have the trans being basically the opposite to this one. So these 2 are actually enantiomers, but these 2, what we see here, that the trans versus the cis will basically be the diastereomers. So these 2 are diastereomer compounds. And in fact, let me remind you, the previous recording had already the question that was on the dimethylcyclopentane, but in that example that was presented to you, it was the 1,3-dimethyl. This one is the 1,2-dimethyl. So it's the same behavior that's going to be for these compounds. Same thing we use when it comes to chiral 3D compounds, we could also use when it comes to Fischer projections. What is that supposed to mean? That means If I have a Fischer projection that is already being labeled S and R, why is it an S? Well, bromo, bottom carbon, and then the methyl. So you have a clockwise, fourth group is up, so that's why it's an S. Chloro, top carbon, and then methyl, so it's a counterclockwise. Fourth group is up, so that's why it's an R. So S and R, when I look at this Fischer projection, what do I notice? I notice that the BR is still there. So this chiral center is the same exact one as this one. It's not the mirror image. But the bottom carbon, it's the mirror image. So what happens when I have an SSRS? These two, it's a pair of diastereomers. So that's basically how we look at it. What if I want to get the enantiomer of this structure? What do? I flip the bromo with the hydrogen, and I do the same thing with the chloro and hydrogen. So the structure that's going to have bromo, chloro on the left-hand side will be basically the enantiomer of this structure. So that's important to keep in mind. And this is the formula that we were just talking about. So when you have two chiral centers, that means I have 4 possible stereoisomers, and those 4 possible stereoisomers would be the R and R, SS, and RS, SR. You're automatically going to notice that these 2 would be enantiomers, and these 2 would be enantiomers, and every single one of those would be a diastereomer of every single one on the other group. So that's important to keep in mind. And the meso compound, we've already seen how it is for 3D structures. How about the Fischer projection? If I have a compound that's drawn in the Fischer projection format, and I can see clearly that I have a plane of symmetry, even though I have chiral centers in it, but the plane of symmetry automatically will make this compound basically the meso identical to the other structure that has the bromo on the right-hand side. So the 2 bromo groups being on the right-hand side versus this one would be the same exact compound. Same thing applied on this tartaric acid. This compound basically, it does have a plane of symmetry. That means the other structure where the OH groups on the left, that I would think it's the enantiomer of it, it's actually the meso compound. So these 2 would be the same, would be achiral compounds. So that's important to keep in mind. Absolute configuration and relative configuration, these are 2 terms that we have to actually be familiar with. When it comes to chemical reactions, I may end up having a new chiral center being resulting in the final structure of the reaction. And that's where I would be basically studying the stereochemistry using a polarimeter to define the absolute configuration. When it happens that I start with a starting material that has already a chiral center, and I'm generating a second, then I will be basically studying the relative configuration. I will be looking at what I started with and comparing it to the new chiral center. So that's basically the 2 terms that we are looking at right here. So here's the examples that we were just looking at. The Fischer projection, these 2 would be enantiomers. There is no plane of symmetry. But these 2 that you would think they are enantiomers, because of the plane of symmetry, they are actually the same compound. So they are meso. But every single one of those would be a diastereomer of any of these 2. And same thing applies on the other structure. So this one and that would be diastereomer. This one and the other would also be diastereomer. So this is just a way to visualize Fischer projections, being able to define the chiral centers and being able to tell which of them are chiral, which of them are achiral. And those achiral compounds, most of the time, they are actually meso compounds. We talked about the stereomers versus enantiomers. It's very important to keep in mind that enantiomers have same physical properties and chemical properties, but they are opposite to each other when it comes to rotating the plane polarized light, while the stereomers are different in physical and chemical properties. So that's important to keep in mind. So if I have an experiment and I have at the end of it 2 structures that are enantiomers, and this is where this chemical resolution of enantiomers topic becomes really important, that we may deal with a compound out of those two enantiomers that is a biological active compound, while the other one is totally inactive. And that's a very common task when it comes to drug industry, that they will run chemical reactions and they will end up having a mixture of enantiomers. But one of them is the one that needs to be delivered to the patient, while the other one, if it was left there, because it's an inactive compound, it will be considered an impurity, and it may be actually a toxic compound. So Louis Pasteur, this man came up with a method that's the chemical resolution of enantiomers, where if I have a mixture of enantiomers, I can basically separate them using physical properties of the corresponding diastereomers. What is that supposed to mean? I'm starting with an enantiomer. How can I make a diastereomer out of it? Here's an experiment. S-butanol mixed with R-butanol. So I have a mix of enantiomers. I react them with a chiral compound. That's the resoluting compound. It's already defined chiral centers. What basically, it's a tartaric acid. This tartaric acid is going to react with both, ending up having what? Having RRS and having RRR. What are these two now? They are diastereomers. And we already know when you have a pair of enantiomers, they are the same in terms of physical and chemical properties, except rotating plane polarized light. But when we deal with the stereomer, they have different physical properties. So how do we take care of this now? Once we react the mixture of enantiomers with a chiral compound, I will end up having two diastereomers that I can easily separate using column chromatography. So this column chromatography basically has a silica gel. This is basically a medium where once I run the two structures now, I will basically have the ease of separating those two based on their different physical properties. And then once I'm done with that, once I separate the two, I basically run some reaction to recover the chiral compound that I was using to separate the two enantiomers. And that's how this method basically is done. Nowadays, they have what we call chiral column chromatography, where basically this chiral compound that I have to react with the mixture of enantiomer, it's already there in the column, meaning when I throw in the solution of the two enantiomers, this chiral material will detect one of them to basically run it faster than the other. And that's basically how we separate those two enantiomers. And this is the most common method actually nowadays being used in the drug industry, where they basically, once they make that mix of enantiomers or the racemic mixture, they separate them using chiral column chromatography. And that's the story of chapter 5.